Physics Challenge 4, Electrical Characteristic. Now we consider the parallel capacitor here, area S, and the electric material has epsilon and distance d. Okay, so according to physics textbooks, the energy stored is given by this, and this is volume integral to get total Q. So if you apply this directly, it's going to be, that's the energy stored. Okay, but this is wrong. A lot of description and the tutorial in internet, they say this is the answer. This is wrong. Okay, if you ask electrical engineering, they said energy stored is going to be VQ. What's happened to this 1/2? Okay, you have to think about where this formula come from. You can't just use a formula without understanding where it's come from. Okay, this formula is based on, say, delta Q moving, and you have already Q accumulated. Okay, so it has this electrical field. So moving this against the electrical field, that's the work performed. Okay, so in this case, work performed is going to be 0 to Q, and you have E and dq move. You move the amount of charge against the electrical field. This electric field is caused by the charge accumulated here, so it's going to be V over L, and that's translate V is going to be let's see, Q over C. So amount of charge dq, so we get LC Q square. So that's where this 1/2 come from, this integration. Okay, but you know, you are going against this charge here, but capacitor has negative charge here. When you separate dq, immediately you get negative charge, and this is gonna pull this back. So actually E need to have 2, so it's going to be like that. Okay, so the real energy stored in this capacitor should be this one, not this one. A lot of people in the internet said this is the answer. That's wrong, because that's only for one side. You have 2 sides for the capacitance, so you have to double the amount. So actually this is the answer. Okay, and electrical engineering, they know that. They always use this for capacitor. Okay, so you can't just use the formula you remember and apply it without understanding where this formula come from. Formula comes from the work, total work, that's the energy. And in this case, if you have an isolated, in the previous video we did this isolated sphere and move dq from far away to this conductor to charge up, then it's going to be 2E d d volume integral. So we have 1/2 in here. Okay, but this is isolated conductor. We're talking about pair of conductor, the opposite polarity. So we have to double it. So this is the answer. Now, you see some argument about the capacitor fallacy or contradiction. They said, suppose you charge V to the capacitor, and you have energy, charge VQ. Well, some of them said 1 over 2 VQ. It's already wrong, so don't rely on those internet sites. VQ. When you turn on the switch, what happened is Q is spread, become half Q, and the voltage is half. So 1/4 QV. Originally we had QV. So 1/4 times 2, we have only half QV. So what happened to the energy? We used to have a QV energy, now half QV. What happened? This is a violation of conservation of energy. Well, actually you have to realize that energy is lost when the current flow here. Just like, say you have this much water in a tank, and you move half to here, and you have only half left. Are they same energy? No. This potential energy is higher than the sum of these two energy, right? Because this potential energy is much higher level. So what happened when you connect a pipe, water flow into this? It's called irreversible process in thermal engineering, the thermodynamics. Irreversible means you lost energy. Loss of energy. Okay, so where this energy lost? Well, if you have a turbine here, you can generate energy. You can recover some energy. Otherwise, all the energy is wasted by friction and the movement of water. Okay, same thing happen here. When you flow the electricity here, well, if you have a lamp here, then this lights up, so you utilize some lost energy by lights, right? But if you don't have any, the current flow into this conductor, but its ideally conductor actually has some resistance, and it's all changed to the thermal energy. So you actually lose energy by doing this. Nothing strange about it. There's no reason to conserve energy from before and after. Okay, you lose energy because you flow the current. Probably the energy lost is going to be the thermal energy, or if you have the lamp here, it's become light energy. Same thing here, the water. So it's an irreversible process here. If you have a half volt to capacitor, can you somehow change to volt and 0 volt here? This can be done. This direction cannot be done. It's not reversible because energy is spent somewhere. Friction for the water, the thermal energy, the heat generated by resistance in the conductor, whatever. If you say no, I'm going to use 0 conductors, then what's happened? It's going to be the huge current flow, infinite current flow, the moment you turn on. Okay, and this is going to explode. That's the energy used. So actually there is energy loss, and people are puzzled by this capacitor paradox. They don't understand engineering very well. Okay, I hope you enjoyed this video. Please check out those physics challenge videos, and if you like, subscribe.